Hello everyone, I'm Oscar Karnalim from University of Newcastle, Australia, and also from Maranatha Christian University, Indonesia. And on this occasion, I will present about my research entitled Common Code Segment Selection, Semi-Automated Approach, and Evaluation. I'm also with Simon from University of Newcastle, Australia. First, the background. So there are two common ways of breaching academic integrity in programming, and both of them are about reusing other people's code without adequately acknowledging the source. It is called programming collusion if the reuse is made with the knowledge of the original authors. Otherwise, it is called programming plagiarism. Both should be detected so that the perpetrators can be penalized, cautioned, or appropriately advised. In detecting programming plagiarism and collusion, usually there are two steps. First, an automated code similarity detection tools initially selects student programs with undue similarity. And after that, the instructors confirm whether the program similarity is a result of academic misconduct. But there is an issue here. Not all code matches in the flag programs are useful for raising suspicion. Some code segments are so common among student submissions that their similarity cannot be used as evidence. For example, code for trivial tasks like inserting into a linked list. Code required for successful compilation like Java import statement. Or starter code provided by the instructor. Removing these code segments from consideration expedite the manual observation, because only code matches that raise suspicion are marked, and this might also improve the accuracy of the detection. In response to that, several similarity detection tools accommodate the removal of predefined common segments. But it introduced another problem. It is time-consuming because not all instructors are used to manually selecting these segments. A few similarity detection tools automate the selection process and directly exclude the segments from consideration. It is based on the frequency of occurrence among student submissions. But it introduced another issue. It is prone to false results because the selected segments are directly excluded without manual validation, while the selected criteria might be unsuitable for the assessment design. So in here, we propose a solution, a semi-automated approach, which means the segments are still selected automatically on the basis of frequency of occurrence, but after that, they are subsequently checked by the instructor before being excluded from similarity detection. This is to ensure the segment's well-formedness, correctness, and completeness. We also propose C2S2, Common Code Segment Selector. This is a standalone tool to facilitate the selection process. Why? Because existing automated selection techniques are not detachable from their corresponding similarity detection tools. C2S2 is featured with several adjustable selection constraints to retain only appropriate segments and to keep their number reasonably low. C2S2 can also directly remove the common segments from student submissions if necessary. This might be useful for similarity detection tools that are not able to exclude such code from consideration. Of course, it is as long as the tools are able to deal with uncompilable code. As an additional contribution, we also propose evaluation metrics. Because existing automated selection techniques have never been evaluated independently. They are evaluated either not at all or in combination with their similarity detection tools. It is difficult to isolate the impact of the technique. C2S2 basically works in 4 steps: tokenization, generalization, segment selection, and subsegment removal. The tool, the documentation, and the code are available on GitHub. You can see the link on the screen or in the paper. First, tokenization. So it is based on ANTLER, in which comments and white space are removed. If one submission comprises more than one code file, the token strings will be concatenated. Second step is generalization. So at this step, identifiers, constants, and some primitive data types are renamed based on their corresponding type. This is to mitigate the impact of superficial variation, like variable renaming, or setting the constant from 0 to 1, and something like that. Of course, identifiers that act as keyword for third-party libraries should be retained, and it can be done by listing them as user-defined keywords. The third one is segment selection. So at this step, common segment candidates are formed by concatenating any n adjacent tokens and retaining only the distinct ones that occur in at least k% of submissions. For efficiency, the range of n should be defined. We also introduced 2 filters to further reduce the number of candidates. First is prefix filter, so that only segments that start with a keyword or an identifier are considered. The second one is line filter. Only segments that start at the beginning of a line and end at the end of the line are considered. Both assume that common code segments comprise one or more complete program statements. The fourth step is subsegment removal. So in here, all candidates that are parts of longer candidates are removed to retain only appropriate common segments as the output. For evaluation metrics, we have 5 metrics, 3 for effectiveness and 2 for efficiency. For effectiveness, we have partial recall, partial precision, and partial F-score. For efficiency, we have number of SIGCSE common segments and execution time. I will start explaining partial recall first. So basically, it is derived from recall, the proportion of actual common segments that are suggested. But it is considered as partial because the measurement is at token level instead of segment level. Why? Because complete segment matches are likely to be rare. The selection of SIGCSE segments is based on arbitrary position and length. Some SIGCSE segments might be longer or shorter than their actual counterparts. You can see the equation on the screen, but I won't explain the detail. You can read it in the paper. The next one is partial precision. This is the counterpart of partial recall, focused on the proportion of SIGCSE segments that are actually common. Unfortunately, this metric might be unhelpful for automated techniques applied in a semi-automated approach, because high precision is often achieved by excluding actual segments with low relevancy. It is preferred to have all actual segments suggested, since manual observation will be performed afterward. Partial F-score, it is the combination of partial precision and recall, calculated as displayed on the screen, but it is only useful if both precision and recall are applicable. Next, the number of suggested common segments. So having fewer suggested segments might expedite common segment exclusion in the similarity reason tool, given small size of the input. It might also simplify the manual validation process and mitigate the mental burden. The last one is execution time. So some automated selection techniques generate the candidates based on any possible concatenation of n adjacent tokens. This kind of process can be time-consuming especially if many variants of n are used. We have 6 evaluated factors of our automated selection techniques, and I will explain it later in detail. And the impact of each factor is measured by comparing the introduced evaluation metrics with the default setting and after removing or modifying the factor. In here, default setting means apply all of the 6 factors. The inclusion threshold is set to 50%, and the range for acceptable common segments is 10 to 30 inclusive based on our evaluation. And this kind of scenario result in 81% partial recall, 6 suggested segments per assessment on average, and 20 seconds of execution time. For evaluation, we have 95 Java assessments with 1,199 student submissions. We also have 8 Python assessments with a total of 479 student submissions. They are obtained from various offerings of introductory programming. Unfortunately, this dataset is not applicable for partial recall because there is no information about the genuinely common code segments for each assessment task. It will be time-consuming and labor-intensive to define the segments manually. Consequently, we use another dataset for measure partial recall. It is adapted from a dataset for evaluating the effectiveness of academic code similarity detection. 7 Java original code files have been disguised to 355 code files. This disguising process can be seen as comparable to completing an assessment with that original as the starter code, which result the original files as the common segments. It is worth to note that not all datasets for evaluating code similarity detection are applicable for measuring partial recall. Most of them provide no information about the sources of copying, which are necessary to establish the actual common code segments. Now we will start discuss about the findings of the evaluation, but I won't explain about the numbers. You can see the numbers in the paper, and in here I will only focus on the generalized findings. First, token generalization. So it basically keeps the partial recall height while suggesting more common segment. Without this kind of feature, many potential segments are not considered as common because they are often found with different surface representations, especially different variable names. Token generalization does not really affect execution time. And the second one is inclusion threshold, or K%. So as you can see in the figure, partial recall decreases as inclusion threshold rises. Higher threshold result in stricter condition for a code segment to be considered as common. In terms of efficiency, increasing the threshold result in fewer success segment, with the most substantial reduction from 0% to 10%. The pattern is somewhat similar in terms of execution time. The third one is prefix filter. So removing this kind of filter does not really affect either effectiveness or efficiency. Further observation shows that segments filtered by this kind of filter are also filtered by line filter, the counterpart. Many common segments that start with a keyword or identifier are also complete lines. But if it is compared with a scenario without either filter, prefix filter alone substantially reduces the number of successive segments and execution time, with a slight offset in partial recall. In other words, this kind of filter might be useful for dataset in which common segments are unlikely to be complete lines. Line filter substantially reduce the number of SIGCSE segments and execution time, because without this kind of filter, segment candidates are formed at any arbitrary position and length. But this kind of benefit comes with a slight reduction of partial recall. Still, it is okay. Next, the impact of retaining only code segments with a particular length range. So in here, we set the minimum length as 10, which is the approximate number of tokens for one Java program statement. And we have 10 tasted range variants from 10 to 100. And as we can see in the figure, once the range is greater than 20, it does not really affect the partial recall. Because in our dataset, code segments that are longer than 30 tokens, 20 per plus 10, are likely to be rare. In terms of efficiency, expanding the range slightly reduces the number of SIGCSE segments, because longer segments often incorporate shorter segments, which are then removed in the end by the subsegment removal. The greater range also results in longer execution time, though the change is not really substantial. In terms of subsegment removal, it substantially reduces the number of SIGCSE segments, because many overlapping segments introduced by the n-gram mechanism are removed. This does not really affect the execution time, as the removal is linear in time, but it slightly affects partial recall. We also compare our proposed technique to n-gram-based technique. It is the basis of existing automated selector techniques. It concatenates n adjacent tokens for any possible n and selecting all segments that occur in at least half of the submissions. We are unable to do direct comparison as only one related work is featured with technical details, and that requires a considerable amount of data for learning the pattern. As we can see in the table, our proposed technique is substantially more effective and efficient, and the number of SIGCSE segments is reasonably low for manual observation. Conclusion, this paper proposed three things. First, a semi-automated approach for selecting common code segments for exclusion from code similarity detection. Second, an independent tool for selecting the segments. And third, evaluation metrics to evaluate automated selection techniques. We have two findings. First, all factors applied in our automated selection technique are beneficial, and the selection technique is more effective and efficient than the n-gram-based technique. We have 4 limitations that result in 4 future work also. First, the tool cannot deal with syntactic variation, which means that program statement generalization should be introduced at tokenization stage. Second, the tool covers only Java and Python. More programming languages should be covered. Third, the semi-automated approach has not been evaluated from the point of view of instructors. This kind of evaluation is necessary to complement the technical evaluation reported here. And last, evaluation datasets are drawn from introductory programming courses. To ensure the validity, the study should be replicated with datasets from other programming courses. In case you are interested to know further about which code segments cannot be used to reduce suspicion, you can refer to this working group report, Choosing Code Segments to Exclude from Code Similarity Detection. It is published from ITC 2020. Thank you.